Hello, my name is Anubhav. I'm a PhD student at DTU in Denmark and with Vito in Belgium. I will discuss how we can harness flexibility from the coordination between electricity and natural gas systems to accelerate the transition towards more renewables in power systems. Operational flexibility in power systems is largely provided by gas-fired power plants, which lie at the boundary of electricity and gas sectors. Moreover, since gas is a compressible fluid, line pack, which is the short-term storage of gas inside pipelines, can be a great source of flexibility as well. This flexibility is relatively untapped. Let's look at this model of a gas pipeline between nodes M and U. QMU denotes the flow of gas across the pipeline. Pressure M and pressure N indicate the nodal pressures that are usually bounded by physical limits. If you look at the graph above, the pressures at the terminal nodes can be modulated such that the same flow is obtained for any path that is chosen between the two bold lines shown. The shaded gray area inside the curves is called line pack flexibility, and it is proportional to the average pressure of the terminal nodes of a pipeline. Looking at absolute numbers, the amount of line pack flexibility is at least 25 times larger than the pumped hydro storage capacity throughout the whole of UK. This highlights the scale of untapped line pack flexibility that can be harnessed just through coordination between power and gas systems. Power systems across the world are evolving such that renewables supported by the flexible generators such as gas-fired power plants are replacing coal. This interdependence between the gas and power sectors means that gas operational constraints are becoming more and more relevant in the day-ahead power dispatch problem. Moreover, short-term uncertainty propagates from the power systems to the gas side, which causes congestions in the gas network, as well as results in unavailability of the fuel for the gas-fired power plants. This, in addition to endangering the reliability of gas supply system, also hampers the amount of flexibility that it can provide to power systems. That brings us to our research question. How do we model this uncertainty propagation and to develop a unified coordination mechanism that reveals short-term flexibility from the gas system? The answer lies in stochastic power and gas dispatch. We consider a fully coupled power and gas system such that a central system operator dispatches both the power and the gas systems. In a generic form, we can write the joint optimal dispatch problem like this. The objective function here minimizes the expected cost of operation for the power production and gas supply. The decision variable x tilde contains the decisions such as production from various generators, nodal power injections in the electricity grid, so gas suppliers injections, as well as the gas network variables such as nodal pressures and flows which are needed to operate the line pack. We write the inequality constraints G of I as distributionally robust chance constraints defined over an ambiguity set pi. We assume that the true probability distribution of uncertainty faced by our problem comes from within this ambiguity set. The parameters epsilon denote the violation probability for each constraint. These inequalities involve generator production limits, gas supply limits, power flow limits in the lines, and similar engineering constraints. The functions h of g are linear in x and ensure the balance of gas and power in the system, and they capture the intertemporal dynamics of operating the line pack. Lastly, the functions wk are non-convex quadratic equality constraints, which is also known as Weymouth equations. These equations govern the physics of steady state flow of gas in a pipeline as a function of difference in squares of pressures at the terminal nodes. There are two issues with this problem in its current form. First, the variables are stochastic, which makes these constraints infinite dimensional and the problem becomes unsolvable. Second, the non-convex Weymouth equations are needed to be convexified in order to ensure global optimality is reached. I will now discuss how we tackle each of these challenges. First, to ensure solvability, we adopt moment-based ambiguity sets for our uncertainty. Assuming that wind forecast errors are the only source of uncertainty, we define ambiguity set pi that contains all probability distributions which have a given mean and covariance. We assume that the mean and covariance are available through analysis of historical forecast errors. To mitigate the uncertainty in real time, we adopt recourse actions for flexible agents in the form of affine policies. Optimal affine policies are obtained already while solving the day-ahead dispatch problem. And thus we reduce the cost of redispatch, which needs to be done closer to real time. I'll illustrate the affine policies through a simple power network setup. Here we have 2 wind farms, 3 flexible generators, and 1 inflexible load. During the real-time operation stage, wind farm production W tilde is made up of day-ahead forecast W hat and some random forecast error omega that is realized. Depending on whether there is a surplus or deficit in the system, flexible generators increase or decrease their production, which balances the forecast error uncertainty in the system. The 2 equations which ensure supply-demand balance in the system are shown here. While the first equality ensures balance in the case of perfect forecasts, the second equation ensures exact activation of flexibility during real time to counter the random forecast errors. Secondly, we assume that the changes in flow in power and gas networks can be approximated through similar affine functions. By adopting these affine recourse actions and following the well-known Chebyshev's conic reformulation, we convert our infinite dimensional problem into convex second-order cone constraints. To handle the stochastic non-convex Weymouth equations, we define auxiliary variables gamma and rho, which are the sensitivities of gas flows and nodal pressures to uncertainty. Expanding the equality and then separating the terms which are independent and quadratically and linearly dependent on uncertainty, we obtain 3 separate equalities. For the first 2, we relax them using the standard second-order cone relaxation, neglecting the non-convex inequality as shown in the figure. The same strategy, unfortunately, cannot be applied to the last inequality because of the presence of the bilinear terms. As a result, we replace each of these bilinear terms with the McCormick envelopes. Adopting these 2 steps, we have now relaxed the non-convex Weymouth equations into second-order cone and linear constraints, making the overall problem convex and solvable. We obtain the final tractable form. It is a second-order cone program that is solvable very efficiently by off-the-shelf commercial solvers. Mean and covariance of forecast errors, which are extracted from historical data, are used by the central system operator to assign not only the optimal dispatch, but also optimal flexibility procurement in the form of affine policies. The parameters epsilon are chosen such that they represent the risk preference and risk tolerance of the system operator, and consequently 1 minus epsilon becomes the confidence level that the chance constraints hold. To test our methodology, we select a IEEE 24 bus reliability test system coupled with a fictitious 12-node gas system. 7 out of 12 generators are gas-fired, and we have 2 wind farms in the system. On the gas side, we have 2 gas suppliers which inject gas into the network. We obtain the bounds for defining the McCormick envelopes by solving a deterministic version of the problem by assuming perfect forecast of wind farm production. We assume that all the chance constraint violation probabilities are identical. And finally, we use 1000 wind forecast scenarios for wind farms located in northern Denmark to compute the mean and covariance. The figures here show the coupled power and gas networks. The gas-fired generators, which link the 2 systems together, are enclosed in red rectangles. Coming to results, the figure shows how the optimal dispatch and affine policies for the power generators look like. These generators have been grouped into gas-fired and non-gas-fired power plants. It was observed that in the hours when specific generators are not dispatched at all, or if they're fully dispatched, they're not assigned any affine policies. Similarly, lower cost flexibility sources are preferred. Similarly, on the gas side, we observed that the most expensive gas supplier, K3, does not get dispatched or assigned any affine policies in the earlier hours of the day. Moreover, the gas injections in the early hours of the day ensure that enough supply is available for the gas-fired power plants from the line pack during the later hours. Finally, it was observed that not only cost, but also the spatial correlation of uncertainty and relative location of the flexible agents decided the allocation of affine policies, which is a very nice result. To test the exactness of the convex relaxations we adopted in the solution, we use a metric that we call the normalized root mean square relaxation gap. It's calculated like this. For a constraint x MUT equals y MUT, which is relaxed to x MUT less than equals y MUT, we compute the root mean square relaxation gap by using the optimal values obtained by our day-ahead dispatch problem. They are then normalized by the right-hand side of the original equality constraint and aggregated to obtain this metric. For epsilon equals 0.05, for the second order cone relaxations, we obtain the following relaxation gaps. The charts here show the normalized relaxation gap for each pipeline for every hour of the day. In general, the relaxation obtained for the uncertainty independent terms of the Weymouth equation, which is shown on the left-hand side of the figure, are satisfactory. However, the remaining gap in exactness can be attributed to the structure of the gas network, which is non-radial. Also, the intertemporal dynamics of the line pack, and in particular, the constraint which ensures there's sufficient line pack available for the next day, they require unusual gas flows at the start and end of the day. This is more pronounced for the equality obtained in the second curve obtained from the quadratic terms of the uncertainty. For the McCormick relaxation, as expected, we calculated the bounds trivially and they are quite loose. This results in higher relaxation gap. Moreover, we also have adversely negative values of gamma and rho for certain hours for some pipelines, and that results in the normalized relaxation gap to exceed the value of 1. To evaluate the quality of the dispatch solution and to choose the right epsilon, we performed ex-ante simulations to estimate the violation probability for chance constraints. Fixing the optimal dispatch and affine policies that we obtained, we used 1000 wind realization scenarios distinct from those used to estimate the mean and covariance to test the feasibility of the constraints in real time. We defined an indicator function that takes the value of 1 if at least one constraint is violated in the given scenario. Aggregating and normalizing this by the number of scenarios gives the ex-ante violation probability. The figure here on the left shows how, with increasing desired confidence level, the ex-ante violation probability, which is shown in vertical bar, reduces. However, the cost of dispatch, shown by the line marked with filled circles, actually increases. And this, in turn, represents the trade-off of risk preference versus the dispatch cost for the system operator. To understand the constraint violations even further, we studied the susceptibility of the individual groups of constraints, such as generator production limits, pressure bounds, and so on, for different values of epsilon. We observed that the power generation limits, the gas supply bounds, and the unidirectionality of the gas flow that we assumed are most susceptible to violations. These results, however, are very network specific. To conclude, in this work, we performed a tractable reformulation of stochastic joint power and gas dispatch based on affine policies. We showed that cost-efficient dispatch and flexibility procurement from a variety of agents can be performed, keeping the spatio-temporal uncertainty in mind. As next steps, we would like to drop the assumption of affine response by network variables and consider generalized decision rules. Also, we would like to tighten the convex relaxation through iterative algorithm and other mechanisms. Further, it would be vital to consider bidirectional gas flow model. It would also be nice to extend the coordination to a market context. Out-of-sample simulations are also needed to evaluate the effectiveness and to provide guarantees of optimality and feasibility for our problem. Finally, instead of the coupled power and gas system, it would be nice to consider coordination with limited information sharing. Thank you for your attention.